So we just finished the proof that for any bounded sequence at all, regardless of whether that sequence converges or not, for any Sn which is bounded, if I divide that sequence by n, I get a convergent sequence necessarily. So bounded divided by n gives us convergent. And the way we did it was writing out the definition of convergence for Tn. This is a thing we're going to have to prove, and therefore it structures our argument. We started by doing some algebra on the inequality. Tn minus 0 is less than epsilon. So we said, all right, well, what does that really mean, not about Tn, but what does it mean about Sn? How do I rediscover absolute value of Sn out of this inequality that will give me a toehold into using what I know about the S sequence, namely that it's bounded? And so we find out that Tn minus 0 in absolute value is equal to the absolute value of Sn divided by n. So the question is, for what little n will this inequality be true? And you find out that because the absolute value of Sn is less than or equal to some constant m, that will let you take this quantity and make it less than or equal to m over n. And that's nice, because now we have n in only one place, right? And everything else in that inequality is going to be a constant. And we find out that as long as m over n is less than epsilon, this original inequality will be true. And m over n is less than epsilon as long as n is greater than m over epsilon. And that is where we get our capital N from for this proof. Right? So in the proof, we come in and say, let epsilon be arbitrarily chosen. We have no control over that. But we do know that the S is a bounded sequence. And therefore, there exists a capital N such that the absolute value of Sn is less than or equal to capital M for all natural numbers n. So every term of the sequence is less than or equal to capital M in absolute value. And that gives us the material that we need to define our natural number capital N such that capital N is greater than m over epsilon. By the way, this is an invocation of the Archimedes principle again, right? Because m over epsilon is real, we know there's a natural number which is larger. That's Archimedes in the background of this proof, as it is in so many of our proofs. And then once we've chosen the capital N in this way, the universe comes back in and chooses for us a little n, which is greater than or equal to that threshold, that capital N. And then we run our inequality argument one more time. Yeah, so this was our scratch paper. This is actually part of our proof. The absolute value of Tn minus 0 is equal to the absolute value of Sn over n. And that in turn is less than or equal to m over n because the Sn's are bounded. And that is less than m over epsilon. Because the n is greater than or equal to capital N, which is greater than m over epsilon, we know that n is greater than m over epsilon. But since that's in the denominator, our inequality goes the other way. M over n will be less than m over epsilon. And that's equal to epsilon on the nose, and we've completed the proof. So this is an example, an illustration of a proof that requires us to know nothing about these sequences other than that they satisfy some definitions. Right? That we assume that the S's satisfy the definition of bounded. We have to prove that the T's satisfy the definition of convergent.